Hello everybody, my name is Dak Shingole and I am the owner of Riptide, a non-profit organization dedicated to providing sustainable energy to low-income communities. Our target country as of now has been Indonesia, a country that is in need of reliable energy sources, as of which Riptide is now releasing their latest product, Tide 3000, which is a hydroelectric system made solely from scraps that can be locally available within Indonesian junkyards. Today, I will be showing the blueprints and design model of the system, explaining the procedural steps required to reach that point, the technical skills used in the process, and all of the changes made. Without further ado, let us begin. Before one starts cooking, they must first check the recipe and the steps. Similarly, let us begin with the procedural steps used to reach the final product first, before checking out the blueprints. In this chart, you can see all the procedural steps before you. Step 1 is research. Step 2 is orthographic, or the orthographic projection. Step 3 is the isometric projection. Step 4 is the exploded view. And step 5 is the title block. Step 6 is the video. This chart here is also known as a Gantt chart, and it was made by a famous mechanical engineer known as Henry Lawrence Gantt. This chart is an incredibly effective and efficient way to plan out the procedure because it displays the timeline of completion in a visual manner using colors. For example, it is clearly visible that the research must be completed within the first week as seen by the red box within the week 1 column. This chart also includes columns for the start date and the estimated time of completion, allowing the reader to easily fit the step into their daily schedule. Finally, the chart includes columns dedicated to the materials and tools required to complete each individual step. The steps listed are detailed enough to be followed by any member of Riptide because they are incredibly specific. For example, each procedural step includes the term hydropower systems. This means the individual will not confuse it with another Riptide project. Also, to the right of each step are 2 columns that depict the basic materials and tools required to complete each step. For example, step 2 shows how you will require grid paper and a pencil, a compass, and a ruler to complete this step. It also offers a simple descriptor of each material and tool to any individual that is unfamiliar with these items. Overall, the Gantt chart is an incredibly effective way to plan out the procedure. Now here are some of the images of the design blueprints coming together. You can see the 2 orthographic projections beginning to form, being the top view and the elevation. Now allow me to talk about the technical skills being demonstrated. The 2 skills that were mainly assessed were the ability to create readable hand-drawn orthographic sketches and the ability to create detailed and colored digital 3D projections of the system. These 2 skills are critical to the success of the product because they are essentially what the product is. The product requires 2 orthographic projections of the system, and therefore an important skill would be the ability to make hand-drawn projections readable so the client can understand what is being made. The product also requires an isometric and exploded view of the system, which are both 3D types of projections. Therefore, an important skill would be the ability to make such projections digitally and to make them detailed and colored, seeing as this would provide the most information to the individual reading the blueprint. For the first hand-drawn skill, I would give myself an 8 when assessing myself. The final orthographic drawings, which you will see in a minute, contain many details such as the dimensions of the system and labels for every part of the system. It is also accurately drawn against a scale and can be easily readable. For the second skill of digital 3D projections, I would give myself a 7. The final isometric and exploded views are very detailed and contain the function of each part within the system. It is also organized by color by having similar parts being of the same color. However, I would not give myself an 8 because I only detail one type of specification being function. An improvement to be made would be to list the cost of each part or the methods of creating or obtaining such a part. Here are the final design blueprints for the Tide 3000. As you can see, we have a top orthographic projection, an elevation orthographic projection, an isometric projection, and finally an exploded view. Let's take a look at each one individually. First is the top view or the bird's eye view. Here you can see the projection is hand-drawn and has all the system parts labeled, such as the turbine blades or the stator. It also contains specific dimensions for the whole system and the individual parts of the system. The dimensions are based on the scale in the top right-hand corner. Next is the elevation or side projection. Here you can see this projection is also hand-drawn, and every visible part is labeled, such as the stator or the turbine generator shaft. This projection also contains specific dimensions of the whole system and the individual parts of the system. Similar to the top view, these dimensions are based on the same scale in the top right corner. Third, we have the 3D isometric projection. This was made digitally by the use of a software known as Tinkercad. As you can see, it is color-coded with each part having its own color, such as the turbine blades all being a light blue and the exciter portion being a magenta. The projection also contains detailed annotations for each part which contain their function in the system. Fourth is the exploded view of the Tide 3000. Each part is clearly separated as if the system had exploded, and also each part is labeled with a number, such as the exciter being number 1, the rotor being number 2. The number is then put to use in the title block, in which the materials used to create the part are displayed respectively. Finally, we have the title block. Here you can see it contains the designer name, being Riptide, the name of the system, the date, the scale used, the page number, and finally the material list. In this list, you can see that each item from the exploded view has been noted along with its respective number. It then describes the material needed to make these parts and also where they will be sourced from. Just like how a boat on a river does not know there is a waterfall up ahead. Similarly, throughout the original procedure, I did not know of the obstacles up ahead, as of which a few changes were made to the original procedure throughout the process. For example, the medium of creating the isometric projection and the exploded view changed from SketchUp to Tinkercad. This change was primarily made because Tinkercad is much more intuitive than SketchUp, seeing as it mostly consists of dragging and adjusting shapes to make the system. There was also already a pre-constructed model of the system from the 3D model of the chosen design, meaning I only had to add on to a template. Another major change made was that the title block was created through the means of Microsoft Paint instead of Google Docs. This change was made because Paint offers the ability to make custom designed title blocks using the box option, while the only way to make one on Google Docs would be to insert a table, which does not look as professional. That sums up the video. I hope you did not fall asleep during this presentation, and make sure to stay safe during these times. This is Dakshin Gole signing off. Peace.